In today's video, we're going to be looking at repairing this Astron 20 amp power supply that's on the bench behind me. Now before I get started with the video, there's a couple of things I want to mention. The first is that I'm not an expert by any stretch of the imagination. So this video is really kind of for entertainment purposes only. I'm sure I'm going to make some mistakes, there may be some oversights along the way, so keep that in mind as you watch. So the first thing that we'll do in the troubleshooting process is just put a voltmeter on the power supply's output just to check and see what we're getting. Now the power supply is plugged in and turned on at this point, so if I probe the two terminals, you can see we are getting 0.355 volts. Now that's not zero, but it's obviously not the 13.8 that this should be putting out either. So that meter reading gives me a few things to think about as far as the troubleshooting process goes. Now of course we saw that there was a reading on the meter. It wasn't completely zero. So that means there's still some amount of power being produced by this power supply. What that indicates to me is that the main transformer that's inside of here is probably okay. I'm ready to pull the cover off and take a look inside the power supply. I'm also going to see if I can find a schematic for this thing online and get an idea of what the circuit looks like. I went online and I was able to find a schematic that should be fairly close to my power supply. You can see over here on the left, this is the transformer. The bridge rectifier is here. All of this stuff over here is the regulation and protection circuitry. This over here is an optional battery charge option, which my power supply doesn't have. And then up here are the pass transistors that help the power supply produce large amounts of power after it's been regulated down here. As I already mentioned, I think this transformer is just fine. Otherwise we wouldn't have any power on the output. So what I think I'm going to do is start checking the voltage right here at this bridge rectifier. I'm going to probe these 2 points just to make sure that we're getting something out of the transformer. And then what I think I'm going to do is move on to looking at these pass transistors. I've had these Astron power supplies before, and usually one of these two items is what fails. I've got my meter set to AC voltage right now. I'm going to probe the 2 input pins on the bridge rectifier just to make sure that we've got something coming out of the transformer. And you can see over on the meter we're getting about 35.5 volts. That's about what I would expect it to be. I'm now switched over to DC volts on the meter. I'm going to take my positive probe and touch that to the red wire or positive output on the bridge rectifier. I'm going to grab my negative lead and I'm going to put that on the chassis somewhere. Actually, I'll put it on the negative post on the output side of the transformer. And you can see we're now measuring 23.7 volts. Again, that's about what I would expect it to be and tells me that that bridge rectifier is doing its job. The next thing we're going to take a look at are the pass transistors. You can see there's one here and one here. I'm going to go freehand with the camera here for a minute so you guys can get a better look at what's going on in here. Back here are the backs of the pass transistors that I'm going to look at now. Now you can see here this little brown wire, that's connected to the base pins of each of these transistors, and each one is tied directly together. And then the brown wire goes up here to the regulator board somewhere. Now, down below all these pins, the collectors of these transistors are also tied directly together with sort of a bare wire that you can see right there. Also, the center pin on these transistors is connected to the collector. Now, on this transistor, there's nothing tied to the center pin, but if we take a look at this transistor, there's a red wire. And that red wire also ties to this red wire that comes out of the bridge rectifier. Both of those go off to this point on the circuit board and are tied to the main filter capacitor there. And then each of the emitters of the pass transistors are connected through load balancing resistors to a single point down there also on one pin of an SCR protection device. There's also a red wire connected at that node that goes up and connects directly to the output post on the back of the power supply. Now if I check the schematic, the voltage that's on the collector pins of the two pass transistors should be 23 volts when this thing has no load on it, like it does now. So I'm going to probe that and see what we get. Now I'm going to put one of my probes on one of the collectors of the pass transistors, and I'll grab my negative lead and I'm going to hook that onto the negative output post. And if we take a look at the meter, you can see it's reading 23.6 volts or so. So that looks like it's normal. If I look back at the schematic again, we can see that the voltage on the emitter of each of the pass transistors should be 13.8 volts with no load on the power supply. So I'm going to probe the emitter pin on this transistor, and again I'm going to use the negative lead on the output post to grab a return point, and you can see we're getting that 3.55 volts. So that's definitely not right. If I check the emitter on the other transistor, it's the same thing, 0.355 volts. So I think we've got a problem with these transistors. I'm going to pull them out of here and do a bench test on them to see if we can figure out whether they're good or not. While we're here looking at the pass transistors, I've got to point out that I missed a step here. I didn't check the voltage on the base pin of these transistors. Well, at least I didn't show it on camera. I think when I checked it, it was reading somewhere around 0.7 volts or something, which for whatever reason I thought was normal. Now the voltage isn't listed on the schematic, but it should be probably somewhere around 13.8 volts. Now spoiler alert, this should have been a clue to let me know that these transistors may not be bad, but we'll talk more about that later in the video. I've got the power supply unplugged at the moment and I'm ready to start taking it apart. But one thing to keep in mind is that these large filter capacitors will hold a charge for quite a while. In fact, if I check it with the voltmeter, you can see that it is still got 23 volts there. So I want to discharge that before I go any further so I don't have any nasty surprises here along the way. Now the way I'm going to discharge this is to take a couple of clip leads and connect them up to the terminals on the capacitor, and then I'm going to use a 47 k ohm resistor, just happened to be what I grabbed, and I'm going to connect up the two leads like this. And we'll just let this sit for a little while and the energy will dissipate through that resistor. Now of course the other way and quicker way to do this is to take a screwdriver and just short the two terminals. You'll get quite a nasty crack when you do it, but it'll be done instantaneously. I prefer to do it the polite way and let that power dissipate slowly. Now of course we could calculate this out, but I'm too lazy to do that. But it's been a minute or so and you can see we're down to 11.5 volts and dropping. So I'll wait a couple more minutes and we should be good to go. One final check just to make sure we're at 0. And I think we're close enough, so good to go. To give myself a little room, I am going to remove the screws from this capacitor and get this circuit board out of my way. Now at this point in the video, I have to explain that I made a little bit of a mistake because I was excited to try out a brand new soldering iron I had just gotten. So I proceeded to unsolder all of the wires on the back of the transistors. But as it turns out, all I really had to do to remove the transistors is remove the two screws on the outer body of the case, and they would have come right out. The thing that you see inside the power supply is just a socket. So I didn't really need to unsolder all of these wires. But at least I got to play with my new soldering iron, I guess. I should be able to just remove these two screws on each one, and they should pop right out. Now I'll use a flathead screwdriver to kind of pry behind it, and as you can see, pops right out. Now one thing to keep in mind, there's a little insulation pad or sill pad that goes between the body of the transistor and the heatsink face. I want to make sure that I have both of those and keep them with the transistors so that I don't lose them when I reassemble everything. Now, on the inside of the power supply, you can see that these are just sort of sockets for the back of the transistors. So I'm going to pull these out and set these aside so I don't lose them. Here's the transistor I want to test. I'm going to leave the sill pad on here just for some extra insulation so I don't short my leads to the case of the transistor. Now, at first glance, this thing may look like it's symmetrical, but it's not quite. The pins are located closer to one end of the transistor than the other. And in this case, they're closer to this side. In this orientation, this is the base pin, this is the emitter, and the case of the transistor is the collector. I'm going to start off with the negative lead of my meter, and I've got that hooked up to a green clip lead here, and I'm going to connect this one up to the base pin. Then I'm going to grab the positive lead of my meter, and I'm going to connect the clip lead up to that, and then I'm going to connect the clip lead to the case of the transistor or the collector. And I'm going to make sure I put that under the sill pad so it makes good contact. Now I'm going to turn my meter on to its lowest resistance setting. And right now you can see it's open circuit. Now I'll grab another clip lead and I'll connect up one end to the emitter pin, and then the other free end I will touch to the collector in just a minute. Now what this will actually do is allow the power that the meter puts out to bias the transistor and show us a resistance value if the transistor is good. If the transistor is bad, nothing will happen and the meter will stay in open circuit. So if I connect this to the other lead, you can see we're still at open circuit. But that's at the lowest resistance rating of the meter. What I need to do now is cycle through all of these all the way up to its highest setting and make sure that it stays open circuit. The more power that the meter pushes through the transistor may allow it to turn on. So let's click up here and see what happens. And as you can see right away at 10K, the meter is now showing a resistance of 7.4. And as I cycle through the ranges, the resistance will change. So what this is actually telling me is that this transistor is good. It's not failed. Like I said before, if it had failed, it would have stayed open circuit on the meter regardless of which setting I put it on. Here's the other transistor. Let's hook it up and see what it reads. Although I'm going to have a feeling here that this one's going to be just fine too. And as you can see, we're getting resistance. So this transistor is also good. As I said at the beginning of the video, I'm not an expert. Now, I have fixed some of these power supplies before and replaced a bunch of these past transistors over the years. A lot of times they fail and show the exact same symptoms that I saw here, where the input voltage is good, but the voltage on the output side of the transistor is low or non-existent. But I guess that wasn't the case here. Something else is wrong, most likely in the regulator circuit. So I think what I'll do now is put the transistors back in, solder everything up, and we'll try and do a little more troubleshooting here and see if we can figure out what went wrong. Since the past transistors all checked out good, I got everything put back together the way that it was. Now, just as a sanity check, I want to double check the output voltage and make sure it's still at that low level we saw before I tore everything apart. And as you can see, we're still at 0.355 volts, so same condition. Now, in my experience, the next most fragile part in these power supplies, aside from maybe the transformer, is the IC regulator chip that is located on the other side of the circuit board underneath these solder points here. Now, luckily on the schematic, we have all of the voltages that should be on these pins, so we can easily probe them and see if there's any issues. I'm going to connect up the negative lead of my meter with a clip lead to the negative post on the power supply, and now I'm going to probe starting at pin 1 and see what we get. Pin 1 isn't listed on the voltage chart. When I cross-check the datasheet for the LM723, it shows as no connect in the package, so that should be at 0 volts. Now pin 2 is the current limit pin and should be 13.1 volts. And as you can see, it's much lower, 0.339. Pin 3 is current sense and should be 13.8, and again is much lower, 0.355. Pin 4 is the inverting input. That should be 7.2 volts, but is only 0.433. The non-inverting input is pin 5, That should be 7.2 volts and more or less is. Pin 6 is the voltage reference. That should also be 7.2 and is. Pin 7 is V minus and should be 0 volts and is. Pin 8 is no connection, so that should be 0 and it is. According to the data sheet of the part, pin 9 is V sub Z, but that's no connect on this circuit, so you can see it's negative 0.041 volts. We're just going to disregard that since it's not in the chart. Pin 10 is the V out pin, and that should be 14.8 volts. And as you can see, it's 0. Pin 11 is the VC pin, and that should be 29 volts. And as you can see, that's roughly what it is, 28.4 or so. Pin 12 is the V plus, I assume voltage input pin, and that is also 28.4, which I believe is probably good. Pin 13 is the frequency compensation pin. That should be 16.1 volts, and that's coming out at 0.335. And pin 14 is a no connect, that should be 0, and it is. Now at this point, we obviously have some bad voltages on the LM723 regulator chip. Now that could be because the regulator chip itself is bad, or it could be because something is causing the protection circuitry to pull it down. I happen to have 3 or 4 brand new LM723 chips in this bag, and the LM723 chip that's in this power supply happens to be mounted in a socket, so I don't even have to do any soldering at this point. All I have to do is remove that circuit board, flip it over, and replace the chips. I think that's the next easiest thing to do. I'm discharging the capacitor again like I did earlier in the video, just so there's no issues. And when that's fully depleted, I'll pull it apart and we'll do the swap. Here's a look at the circuit board. I've got it out and flipped over and just temporarily bolted to the capacitor so that you guys can see it. This is the LM723 chip here. Now before I pop it out of its socket, I'm going to make a note where pin 1 is so that I put the new chip in the right way. Now I'll just grab this plastic tool and I should be able to work it out of the socket. I'll grab one of my new chips and then I'll orient it and make sure that I've got pin 1 lined up correctly in the socket. I'm not sure if you guys can see this in the camera or not, but there's a little bit of an angle on these pins. They kind of push out a little bit. So I may need to push these in or just be careful with them as I seat this down into the socket. Okay. Once I'm sure the pins are all lined up correctly, I can just kind of push this gently down into the socket. Okay, I'm going to flip this board over, bolt it back in place, and we'll give it a try. Alright, I'm going to turn the power supply on and we'll check the voltage and see if it's working. Moment of truth. And we're looking good, 13.75 volts. That's pretty close to what it should be. There is a little trim pot in here that I can adjust to get that right to 13.8 where I need it, but that's probably close enough, at least for testing. Before I finish putting this power supply back together and call it completely fixed, I want to go back to something that I talked about earlier in the video that I observed but didn't take into account in my troubleshooting. And that is the voltage on the base pin of the 2 pass transistors. Now I had checked it, and when I did, I think it was reading somewhere around 0.7 volts back when we first opened up the power supply. Now at the time, I didn't really think much of it, assuming that it was low because something was wrong with the transistors. But that really wasn't the case. The voltage was low because the regulator circuit wasn't working right, and because the voltage was low, the transistors weren't turning on and working. But now that the power supply is fixed, if I check the voltage on the base pins, you can see that it is now 14.3 volts. So if I had stopped to think about that a little bit more during my original troubleshooting process, I might have saved myself the time and effort of dealing with the pass transistors and gone right for the regulator circuit. Oh well, lesson learned. This setup is a little bit crude, but I think it demonstrates that the power supply is working. Over here is an old Drake TR72 2-meter ham radio transceiver. It's connected up to the power supply and obviously drawing power and working. Now on the back right now I don't have an antenna, I've just got a dummy load connected up. But if I turn the squelch down, you can hear it's receiving static and working and drawing power from the power supply. You can see the meter right here is showing 13.73 volts output power with the radio loading it. So that's pretty good. And then I've got this little meter down here, which is not exactly the most accurate thing in the world, but is reading 13.6 volts. It's showing a 4-watt draw, 0.3 amps or so, and some other stuff flashing down here. So I think everything is working. Just to put a little bit more of a load on the power supply, I'm going to key up the microphone and transmit with the radio, and we'll take a look at the stats in the meter here. So now you can see we're drawing about 2 amps or so, about 27 watts. The voltage up here is dropped just to 3.72 volts, so seems like everything is working as intended. I tried to do something a little bit different with this video, and I left in the whole part about chasing after the pass transistors and thinking that that was the problem with this power supply. A lot of times I'll edit that type of stuff out of my videos just to keep them a reasonable length. But also, honestly, to save face a little bit. Sometimes us YouTubers don't like to admit that we make mistakes. But I thought it was important today to show you that I make plenty of mistakes. Even if you get to a point where you've found you made a mistake, it's all part of the learning process. It's okay. Take what you've learned, move on to the next thing, and see if you can work past it, which is kind of what I did here. And hopefully it inspires you to do the same thing if you're working on electronics or ham radio. But when you're doing that, don't skip any safety precautions. And if you get in a real bind where you're not sure what to do, make sure you get help from somebody that knows what they're doing. But that's enough for today. I hope you got some value out of this video or found some enjoyment in watching it anyway. 7-3 to the hams out there, and thanks for watching.